Hi. Well, sorry about that. The tape just ended very abruptly when I got to 15 minutes. I just like to continue with showing you the equation that you need to use to figure out the activation energy and the pre-exponential factor um, from the data that you would have taken for the temperature dependence of the rate constant. So working with this equation a little further, the natural log and the e functions are inverse functions of one another. So the log of e to the something is just the something, just like in base 10 logs, the base 10 log of 10 to the something is that something. So in other words, the log of 10 cubed would simply be 3. Just like that. Basically, the log is the exponent in a 10 to the function. The similar thing with natural log. Well, anyway, I'm saying too much about that. This just becomes the exponent. So it's the log of a plus minus ea over r times 1 over t. All right, so what this is, so what we've sort of done here is we have done something called, we have linearized the Arrhenius equation. And let me explain what that means, okay? So what you could see here is if you manage to figure out, to take data for the log of the rate constant as a function of temperature, because T is right here, okay? And if you take 1 over T and you plot that on the x-axis, and you plot the log of the rate constant on the y-axis, then basically using the formula y equals, well, b plus mx. So this is the slope. So if you plot the log of k versus 1 over t, the slope is minus ea over r, and the intercept is the log of the pre-exponential factor. So what does this mean? So this means if you were to get data for how the rate constant varies with temperature, so if you have, several temperatures, like we would have done if we had actually performed this lab, and we would have measured the rate constant for different temperatures, okay? But plotting K versus temperature isn't going to get you anywhere. That's not going to be a line. What you need to do is to plot the log of K versus 1 over the temperature. And by the way, that has to be the temperature in Kelvin. So if you started with this as, the data that you took in your experiment, or the data we're going to give you soon for that, what you'd need to do is you'd have to figure out, first of all, what is the temperature in Kelvin? So using Excel, let's say this is A, and this is 1, 2, okay? So this is A, this is column B, this would be column C, okay? So in this block here, I would literally type equals A1 plus 273.15. Might as well put in extra sig figs. Okay, and then what it would do is it would put the temperature in kelvins in all of these. Then you could copy it down, and you would have the temperature in kelvins in this column. Then what you could do is you could say, okay, let's take 1 over that temperature. So you would type equals, now this would be column C, so equals 1 divided by C2. Oh, this should have been A2, not A1, right? Because this is the temperature in C, and we're taking that temperature in C and adding 273.15 to get it in Kelvin. Now we're taking the reciprocal of the temperature in Kelvin, So that's what you would type here. And then, of course, you'd have to hit return, and then it would put the number in, and then you would copy that down the column. Okay, and then it would fill in with all the temperature, 1 over temperature. And then what you would do in this column, so this would be D, this would be E, is you would say, okay, this is going to be the natural log of K, so you use the equals ln. You want the natural log of what's in B2, and then close the parentheses and hit the return or the enter, and then you'd copy that down, and it would put the natural log of K in all of these places. So then what you would do is you would do a graph. So you would select these two, basically the stuff in these two columns, these two, okay, you would select this. You do insert graph, and so it would do a graph of the natural log of K versus 1 over T, and it would be a graph that would look like this. Well, of course, it would maybe go through the points a little better. Then what you would do is you would find a trend line. Okay, and you would notice that the slope is negative. Well, if you go back and look at the equation here, you see that the slope is the negative of the activation energy divided by R. So you expect it to be negative because activation energies, that's the height of the bump here, they're always positive. So EA is positive, so minus EA over R is negative, so a negative slope is fully expected for the natural log of K versus 1 over T, okay? So, so then what you would do is you would take the value of the slope from the trend line, okay, and you would, then the slope is equal to minus EA over R. So that would mean that R times the slope is minus EA. We multiply both sides by -1, and you would see that the activation energy is simply the negative R times the slope, where R is the same as it was in the unit on gases. Well, it's the energy unit one that we use. We used a couple of different R's in that unit. It's 8.314 joules per mole Kelvin. And if we go back and look at the equation here again, we see that the intercept is the log of the pre-exponential factor. So the intercept is the log of A. So if we take E to both sides, so we're taking the inverse natural log of the natural log, that just gives you the A. A is E to the intercept, and you say, oh, how am I going to do that on my calculator? Well, you will either have an E to the X button on your calculator, or you will have an inverse ln. Sometimes on some calculators it's second ln. You may need to send me a photo of your calculator if you don't know what button to push, something like that. So you'll be able to figure out the pre-exponential factor by taking E to the intercept. This A is going to be a large number. Why is it so large? Well, remember what it is, right? It's got that collision. This is the collision frequency, and you could imagine if we're talking about molecules colliding in a solution, that's going to happen pretty often. So that's a pretty big number. And we have no way of knowing what this P is in this experiment. We're actually going to figure, A is equal to this product of both of these things. But A is going to be a large number. So don't be surprised if you get a very large number for that. Okay, I think I'm going to stop.